So I've gone for the retro slide. So this is one of the original cover slides that I think this is one of Dave's favorite objects. So this is rotavirus. So this is going to be more of a historical look at kind of how eBIC started and what we've done through the years. So it's a 10-year celebration of this meeting. So Pejun asked me to kind of wander through the history. So, okay. So actually what I should say on that slide is the important people who kind of really started the idea of eBIC and getting this grant written and funded and done are listed here. So Dave, Kai, Helen, and is that the 2 CEOs ago of Diamond? So, so why a national facility? So kind of 2012 was, I think, when they started putting grants in to try and get this thing off the ground. We were in the we got the next generation of microscopes with autoloaders, so that was good. We had, software improvements both on the microscope in terms of automated data collection. And Helen has a funny story from one of the trips that we made to Scripps back in the 2000s when she almost, I think, got arrested in Scripps for, was it vagrancy or something? I think, can't remember. Was it Gabe Lander who reported you to the security and said there's a strange lady sleeping on the sofa? So that was the first taste of automated data collection. We had essentially, a bunch of nice data collection software starting to come online, CCP-EM being very important for a development of a lot of things. And we had kind of Relion appearing and, some really nice softwares. And I suppose the biggest kind of thing was the direct electron detectors. At the time, I was kind of in Helen's lab, and we were fortunate enough to get 2 of the direct detectors, and I was doing some comparisons as everybody was doing at the time. So this is from Carson's group, I think, on the Falcon, and we were looking at a K2 D20. And it's kind of, this is really when the crystallographers realized that we might actually be useful. And as I say, apart from Martin, so he tells me anyway. So you're not really meant to take in this. This is just a kind of a timeline from the grant starting in 2014 to where we are now. There's a bunch of lollipops with various bits and pieces on there. So we've got in red, the big instrument installs. We've got smaller instrument installs in, where are they? There we go, brown. So we've got the 200 kV systems. We've got software in gray. We've got essentially detectors in blue. And then we've got everybody's, favorite period from COVID times. So it's just to say that we've constantly been evolving what we do and what we have at the facility. So, yeah. So we'll start off with the center. So we've got the building, the large TEMS, small TEMS, some FIB-SEMS and some CLEM. So Cryos 1, so our building wasn't ready. So in the pictures that you saw for the 2015, you saw the building half built. So what they actually decided to do was install Cryos 1 on the hall floor in the synchrotron. So I think it was a surprise to everybody that this worked as well as it did. So again, coming back to something Alistair said last night. So this was, I think at the time, the kind of fastest Cryos install around. So I think they were pretty shocked that Alan managed to get this done literally a month. It was tested, we accepted it, and the first users were on the following Monday. So, and yeah. And as Alistair always likes to point out, he was first, I was second. So this is the order of, but probably what we should have had is the one above Alan's head because he was there for either of us doing the installs. And so one of the things that I came along to do was do some, commissioning tests. So the synchrotron, generally, when you get a new beamline, the first thing you do is run a bunch of tests to make sure it works, so you can convince your users that it's worth coming. So I used my favorite protein at the time, which again, you'll see much later in Helen's talk, I think quite a lot of GrowEL. So, and this is, with at the time, the Falcon 2 detector, the resolution was not super great. And again, with the K2. And what I would say is this is the time before apoferritin. So I think everybody switched to using apoferritin to characterize any detectors microscopes after this. So 2016, the new building arrived. You can still see there's always something going on at Diamond. So we had a brand new building, so I-14 building. So we share that with eBIC, which is the National Physical Sciences, and a nanoprobe beamline. So from Diamond. So I don't know, this isn't a problem. The healthy problem that we had was that between getting the building commissioned and us actually moving into it, we managed to get money for another 2 cryosysts. So this originally wasn't a hall. This was originally 2 separate rooms. So the first thing that we had to do when they finished the building was to knock down a load of walls and make this into a hall so we could actually fit the microscopes in. So that was all ongoing. We didn't know how long the building was going to take to commission. So Cryos 2 was also put on the hall floor in maybe not such a nice location, didn't quite work out as well, and was a bit more of a painful microscope in general to get up and running. But again, we did that. The first microscope we put into the new building was our Talos, so the 200 gate kV system, and this is Alberto, the installation and engineer. So that was 2016. So then we move on to 2017. We can see everybody's favorite thermo engineer. So this was the installations of Cryos 3 and 4. So essentially, we started off with 3, then 4. So again, we got these kind of both installed in about 6 weeks. They had equivalent specs to 1 and 2. The idea being is that we wanted to be able to do all the different types of experiments on the same machines to make it easier to swap between machines for us and for users. We also, in 2017, got the SIOS. So this was originally installed in Struby, but it was moved to our new building, and we had a loan from WAR, so Corey, who came in and ran the fibs for us, who we subsequently loaned back to WAR after he was with us for a few years. So that's where the kind of fib journey started. So come the end of 2017, we were kind of 4 Cryoses, a Talos, and we had a SIOS. The problem is again, originally we were expecting to have 2 Cryoses. We really didn't have any room to put anybody downstairs. So the next piece of building work we had to do, there was essentially a bit of roof space above the beamline control room. So we managed to commandeer that and build a control room so we could put all of the controls for our Cryoses. This seemed like a really sensible idea to put everybody in one room pre-pandemic. It wasn't such a good idea once the pandemic. Never mind. It is what it is. So we have the fiber solution, and Cryos 1's 400 meters away, and it's pretty difficult to tell. So the other thing, and one of the benefits of kind of working at a synchrotron, is the infrastructure. So this is the SIVL that we had installed. So this was to take liquid nitrogen to all the machines, so we didn't have to worry about swapping dewars on and off and things like that. This, how should we say, has failed in the last year, so we're just in the process of replacing. And then 2018-19, so I think Jason came towards the end of 2017, I believe. And so he was working with the Industrial Liaison Office, so looking after industrial clients. And then essentially we had an agreement with Thermo, so we got another couple of machines. We managed to shoehorn them into the building. So and we were pretty full. So just to say, we do have an industry. And then kind of the last real kind of hardware installs were the Aquilos. So this was essentially Thermo's full kind of cryofib with their own loading station. So, and obviously James was now the man to look after this, looking a little younger and less bearded in this picture. So this came with, cryo lift out and things like this. So, and we essentially acquired, or Peugeot managed to acquire a Leica Thunder. So this is for doing cryoclem experiments. Because we've got so many things in the building, we don't really have the perfect room for that. So we, again, one of the nice things about being at Synchrotron, you have access to engineering. So there's a nice little design for a kind of collar that stops contamination, humidity. And then in 2023, we've also added the kind of in-chamber fluorescent solution as well. So, yeah. And then the last but not least is we've now gone to the massive Dura, which a lot of people have to try and make operation of the Aqualos a little bit more automated and, longer running. So, and, sub-angstrom guys even put you a nice little sticker, so it's fully branded. So this is where we are now. So I've not mentioned the Chameleon. I think Dave mentioned that yesterday. So we've pretty much got a bunch of microscopes. We have a bunch of infrastructure for doing tomography, and we have some smaller microscopes for kind of screening. This is kind of a site-wide resource for the different institutes. And then, yeah, we've got detectors and various things. So now I'll move on to kind of data collection, detectors and processing. So this is where we kind of started 2015, 2016. So we had class 1 with a Falcon 2 and a K2 biquantum. So, 17 frames per second seems kind of pretty slow these days. So even 40 frames. So we were collecting probably in linear on the Falcon 2, maybe 50 to 90 images per hour. And then with the K2, something, anywhere from 25 if you're at super resolution to kind of 60 if you were encountered, and lots of shots per hole. Again, one of the nice things about being at the synchrotron, all this is connected to, a high-speed central compute system. We've got plenty of storage, decent cluster. And we also have access to a tape archive, so everything that we collect is stored for the lifetime of the tape. And we were about 2 terabytes per 48-hour session. And I think this is one of the points I'd like to make. I mean, as part of the original grant, it was something that we kind of negotiated with Thermo that they would essentially incorporate the biquantum K2 into EPU and tomography. So that's something that was a benefit, I think, to everybody who had K2s with bioquantums. And then, you can see by 2017, 2018, there's not really a great deal of difference. So, I mean, we're moving to kind of Falcon 3s, which were a little bit faster and had counting options on there, but the counting option was, very good, but very, very slow. So we were still kind of 120 images linear and, super res about 40. And we're probably, roughly the same size. So this is the journey kind of started for our processing. So we started off with kind of a manual pipeline in some ways using Scipion just to do motion correction and CTF estimation. So again, this is kind of end of 2017. We started with eBIC, which was the kind of web-based front end. So this was to kind of mimic what they had in MX. So they've got a very slick processing pipeline with display in MX, and we were trying to get to that point. Unfortunately, we were just a little bit slow really doing that. We kind of got to the stage of having an automated pipeline in about 2018, again in Scipion, going up to 2D classification. So the next big change was essentially detector upgrade. So this started around 2019. So we managed to get the funds for K3s. So, and these were much faster, they were larger. It meant you could use kind of higher counting rates, which shortened the exposures, which meant you could get to kind of 200 images an hour area. We also started to switch to using compressed formats to help with space. And as you can see, we kind of managed to get all of these installed pretty much within the year. I mean, so we started off with serial EM because obviously the K3 wasn't incorporated into EPU yet. So that was good. The industry guys were trying Latitude, which I think they liked. Yeah, so, and then from there, kind of things started to really kind of speed up. So we've now got a much faster detector. So we're getting up to maybe kind of a 2-3-fold increase in throughput. So, we're getting close to kind of these 200 movies an hour. But then the whole image beam shift data collection started to appear. And again, this was kind of in serial EM first. So this is kind of where, and oh, yeah. What's going on? Interesting. Okay. So this is where you use your stage to move to one hole, you focus that hole, and then you use image beam shift to collect all of the neighboring holes. So this massively increased throughput, and essentially, we were going up to something, if you pushed it, it was around 7 to 800 movies an hour. So we had like a further kind of 7 times speed increase. So again, this was done with serial EM first. So I think Giuseppe gave me the original script for running this at serial EM. So, and they had this on the fly beam tilt correction for when you do the image beam shift. So we also at this point started working much more closely with the CCP-EM guys, using their pipeliner for Rely On. We switched the kind of SPA pipeline to a Rely On based pipeline, and we had some parameters that you put in at the microscope, and then it would generate some nice results for you. And I think, this was along with the use of apoferritin. I think this was Dave's favorite saying is, we are the Institute of Apoferritin Studies. But I think when you work at a facility and you always have to calibrate everything, kind of when anything is changed, you'll end up doing a lot of apoferritin reconstructions. The other thing that we also did was to try and get remote access up and running, and this was particularly important during the pandemic. It meant we were able to run a limited user program. I think I was probably at home for, I don't know, 2 weeks maybe. But generally it works since then. And so this system has really kind of taken off, and a lot of people are still, particularly for single particle experiments, they don't come to eBIC anymore. They just ship the samples, we load, set the microscope up, and then the users do most of the collections remotely. Then the kind of next start of, how should we say, detector season was on Cryos 3. So this was kind of Alistair negotiating with Thermo, Andy helping with the install, and them kind of really pushing this. So we essentially put a Selectress energy filter on a Falcon 4 towards the end of 2020. It was installed between lockdowns, and again, this is getting Alan on site. So he did a lot for us during that period, and we could start to do kind of comparisons again. Apoferritin, it's a wonderful thing. And it's it's a super stable, very easy to set up. So then the next kind of software development was the kind of fringe free. So this again allowed us to reduce the size of the beam that you use to image, because you remove the fringes from the condenser aperture, meaning you can get more shots per hole. So again, you increase throughput, and now with the right conditions, you can, on the K3, you can certainly go to well over 1,000 movies per hour. What's interesting though is that if you look back to 2015, 2016, the visit sizes are still roughly the same in terms of space on disk, because everything's now with the compressed formats. And I think most recently they've just put compressed TIFF on the Falcon 4. So, and obviously the pipelines. So we've been working with the pipelines constantly. So we well, we're in the process of retiring I/B, so we have a new front end, which is kind of written by Guillermo. So hence why it's called Pato, Brazilian for duck, if anybody's interested. So yeah, so this was a user visit that I think was 2 weeks ago. So essentially you get, the resolution estimation from CTF, you defocus parameters, you get your particle count, you'll have 2D classes. So it uses the class selector and rely on, so it'll throw some classes out for you. Once that's done, you'll kind of batch them until you reach about 200,000. You'll run some 3D classification. So we use Cryolo for the particle picking, which I think actually does a pretty decent job with most samples. There are some samples that it doesn't work on, but it works surprisingly well. You can get, a nice 3D. And now, this is Stephen has added this. We're now going on to the next step where this is a kind of a B factor plot, so it's still 2-binned. So just to give you an estimated B factor, and then you can have a refined structure. I think we need to have an isosurface slider on here, so it's the threshold is a little low, but it's at 4 angstroms, 4.3, but this is still bin 2. So, I mean, and literally the only thing that they've had to put in for this is to tell our pipeline what the dose was per frame. Everything else is automated. So if you've got good samples, you can refine structures. Yep. And yeah, no, thanks to Yinghong and Dimitri and Jake for that. And we're also, again, we now have all of the compute data analysis team in place, so we can monitor things. So this is just from the first run this year. So this is essentially the number of motion corrected micrographs. So this is in thousands. So you can see Cryos 2 is the single particle winner. So it's had over 700,000 micrographs motion corrected in about 8.5 weeks, over 2 million in just the first run alone. Okay, so moving on to the last thing, I think I've got about, a bit of time. So again, so this is now more the tomography FibStem side of the facility. So as I say, we started off with the SIOS. So this was some of the initial work done by Corey. And as I say, it was installed at Struby. So this is again from Kai's lab. So these are some of the initial images of lamella that have been cut from the TEM. You can see all these lovely membranes, and I like this bit. It's difficult to successfully cryotransfer to the TEM. So yeah, it's not as difficult as it used to be. You can't keep the crystallographers away, so they see a new bit of kit and they want to put crystals in it. So they devised an experiment to essentially take big crystals, make them smaller, and get very nice diffraction. So there was a nice paper published from Emma on this. So I love the phone screenshot as well. It's a good one, that. And obviously this has been updated, and we've got a bunch of people who are trying to make this work and get it as automated and hopefully as slick as the MX one of these days. It's just, EM people, we all want to be crystallographers, don't we? So but kind of where things really started to change was when we had the Aquilos, particularly after we got over the issues with contamination and, how should we say, the vacuum system having to be rejigged by thermo. So it went from, 6 to 7 nanometers an hour to what? No, actually, was it more like 20? I can't remember now. It was a lot. So by the time you'd kind of fine polished one of your lamella, some of your other ones were, or when you finished fine polishing your lamella, your first one that you did had a nice big thick layer of water on it. So that had to be solved, but really Autotem is kind of what's Thermo have brought to the table for kind of setting up automated milling positions and things like this. And this is really what I think has allowed us to kind of offer a sustainable user program on the instrument. So it's, we can do some training. So James will get the users in, they'll do a little bit of training, and now we, routinely get between 20, 30 lamella per grid. Yeah, so this is one of Craig's samples, who was a postdoc in Pejun's group. And then this is, ideally what we want to do. So this is so I did the tomography on this, hence why the slide's made. And again, thanks to Yehud and Lior. And this was, this is what we want to do. We want to get people in, we want to mill lamella for them, and we want to do some nice tomography and hopefully get as many tomograms of their area of interest. And again, these are just a couple of in-house examples. So this is Dave's rotavirus. So this is a collaboration with James and Dave's group. So this is, some of the early work done on the Selectress Falcon 4. So they see the RNA, you can see everything. And one of the, I think, key things with this work is that they found kind of an intermediate structure that you can't get in a test tube. So this is the whole point, right? In situ is where everybody's going to, because you can't get the structures if they're not in the right place. And then just to say that you can actually do this with a K3 bioquantum. So again, this is from Pejun's group. So this is looking at a membrane protein. So again, subvolume averaging, so fib, some fib, and cryo-ET. And then again, Pejun and Jen, who's got a very, recent paper looking at chromatin organization. So this is, super nice. And this is really kind of why everybody's going to in situ. So I put this in because, well, it's something that we did, which we've never got around to writing up. So this is again with Andy. This is just looking at, with our ideal sample. So Selectress Falcon 4 bioquantum. So this is the whole super resolution still works for tomography. So you can go past the Nyquist if you have an ideal object. So these were both processed with warp. So you can go substantially past the physical Nyquist. So just to say. And then, I think where everything is kind of going now is trying to get the correlative side of things up and running. So Parajat has come to work at eBIC. So she is trying to piece together all of the different things that we have. So the Leica and the Delmic. I mean, this was, started by others, but now this is trying to get this into the workflow so we can, cell's a big place. So if you want to find your object, you need a marker for it. So, some things you want to do, maybe correlation, some things you don't need to. Sometimes you can get away with 2D, sometimes you need 3D correlation. It depends how rare your event is. And again, Patrick is kind of helping out with this with his project. So yeah, so if you want to know anything about that, Parajat's really the person to speak to. And this is where we are kind of now on this workflow. So, and we've pretty much got everything in place to do fully correlative. We're just trying to get all of the images in the right places and trying to make this as streamlined as possible. Because in the end, this is probably where most of the work that we do will go. And just to say, kind of the last real software thing is, again, image beam shift data collections that kind of really help with SPA throughput are now in tomography. So again, this is another thing that, you saw it in serial-EM first, and now it's in Tomo. The latest version of Tomo, they've fixed some of the tracking issues, so this works very well. This again is another test thing that we did on one of our cryo-ET courses. So we collected, so I think, what was it, it's 130 overnight. I've done another one where I essentially collected a whole grid square with image beam shift tomography on a ribosome sample, and I think that got 300 tomograms overnight. I mean, it's not going to work like that for lamella, but yeah, just to say that the throughput. And of course, we've got a web front end for this. So you do motion correction, CTF estimation, RTOMO for reconstruction, and we do have some denoising as well, just a simple denoiser through Topaz. We are looking to work on this to try and improve, and Stephen has done a lot of work on this with Dan. Yeah, and again, we have, we can see which is the favorite tomography microscope. So that's the Selectris 5.4. So again, this is the first run of this year. So 700 tomograms. So not too bad. And then, I just wanted to finish off with a big thanks to the users. So first paper 2015, which wasn't bad for saying we only opened, I think, 3 months earlier. So it's not so bad. And then, we've gone on and the users have had lots of very nice structures. So, yeah. And then, the publications. So obviously we're only partway through 2024, but that still seems to be going up reasonably well. I mean, 2021, I think people had, a lot of stuff that was in the locker, which they had time to kind of write up and do. And then, EMDBs, PDBs. So it's all going in the right direction. And yeah, lots and lots of people. So started off small, kind of slowly got bigger. The pictures changed. Some of the people are still the same. I've had people, yeah, obviously go, leave, and yeah, just and then Alistair, he decided he fancied a different challenge, so he's now trying to persuade people to use high energy electron for diffraction, and he's building a beamline. So, and yeah, and then, well, that's the end, and I don't know about that. That's for you to decide. But there is a job advert if you'd like to join and help make sure that we do evolve at some point. Sorry, I went on a bit long.